Hello guys, welcome back to the series. This is chapter 2 force motion. Uh, in the past lectures we have discussed representations of vectors as well as components of rectangular components of a vector, and we solved an example as well in the last video. This video is about scalar product or a dot product of the two vectors. Before really defining the what the scalar or dot product really is, I think it is better to have a motivation to first see why dot product is necessary. Remember when we were talking about vectors, we gave an example where we had a cart and we were trying to apply some force in a tilted angle, and we were trying to move it, let's say, this way. So we were trying to displace the cart in the right direction. So there's some displacement, and we're applying some force in this direction, this way. In previous videos, we have discussed how the force actually has two components. One is the vertical, and the other is the horizontal, or the one in the right direction. So this force actually has two components, and we're trying to displace the cart in this direction. Now, uh, we discussed in that video as well, when we were talking about how much of this force is actually being used to push the cart in the direction that we are aiming for, which is the direction for displacement. Obviously, because the force actually has two components, the one in the in the y direction, the other in the x. So how much of this force, this total force, which is applied at an angle theta, is going in the same direction as the one that we are actually trying to aim for. So what really happens here is that we're trying to find out how much of force is aligned with displacement, or the direction of the displacement. Displacement direction. Since displacement itself is a vector quantity, so it has a direction as well. So uh, in this case, it is on the right direction. And so we want to find out how much of this force that is being applied on the cart is actually contributing to move the cart in the same direction that we are actually displacement is. जब हम इस तरह के कॉन्सेप्ट पे बात कर रहे होते हैं, तो जब हम ये बात करेंगे कि हाउ मच ऑफ फोर्स इज अलाइंड विद सम अदर वेक्टर, और हाउ मच ऑफ अ सिंगल वेक्टर ए इज अलाइंड विद वेक्टर बी, so we actually talk about scalar product in that sense. Uh, let's see this. So imagine that I have a vector A and I have a vector B. So this is my A, this is my B, and I want to find out how much of this B is actually projected onto A. इसके कितना aligned है with A. In previous videos, we talked about how projection is actually related to cos theta. We talked about it this way कि हमारे पास अगर ये वेक्टर है तो we can actually see the projection of it on the x-axis using cos theta. So exactly that's the scene, that's the case here as well, where we actually see the vector B having a projection on A, and so this projection is going to be B cos theta. But since we are actually seeing this projection onto vector A, so we multiply the magnitude of A as well. So the projection of B onto A is given by AB cos theta, where B cos theta was simply the amount of projection of B onto A. But since we are seeing the projection onto A, the magnitude of A needs to be multiplied as well. That's why we get AB cos theta. And so this is actually written as A dot B, or what we call as a scalar or a dot product. So by definition, this is what scalar product is. It checks how much of a single vector B, let's say, is aligned with or projected onto A. Using the same definition, we can actually now see this example where we talked about uh, how much of force is actually aligned with the direction of the displacement. So we said the F actually has the force, actually in this case this force actually has some angle theta, and it has two components. One of those is going into the direction of displacements. We want to find out how much of it is aligned. So it is simply F t cos theta, and we can also write it as F dot t. Now you might have already recognized that this definition is the definition of work done. Uh, you can actually see this through another example where we have, let's say, this box and you were trying to move it in the right direction. But I was actually putting the force from upwards. Now, how much this force is, we want to find out if we can actually move this box towards right by applying a force from upwards. So, इसका ये भी आप मतलब ले सकते हैं कि कितनी force actually direction of displacement में aligned है. Now, obviously, by just looking at it, we can see कि force जो है वो सिर्फ vertically direction में, and we are trying to move it on positive x direction. So actually, there is no component of force that is actually aligned with the direction d. So obviously, we can't move the box at all by applying a force downwards. We can actually see it this way as well using the idea of scalar product or a dot product, where we see that ft cos theta equals to w or f dot d. Now you see this angle made between f and d here is of 90 degrees. So we put theta equals to 90, and since cos 90 is actually 0, so we get w is equals to 0. So there is actually no meaningful task being done here, and that's why the work done here is also 0. So that really proves it mathematically as well कि अगर हमें बॉक्स को इन डायरेक्शन ऑफ डी मूव करना है और हम उसके म्यूचुअली perpendicular फोर्स लगा रहे होंगे where force is not aligned with the direction of displacement at all, then we are going to have zero work done. We can't move this box at all. But if we had even slightest of angle or slightest of uh, this direction of force being in the direction of the displacement, इसमें tilted तो है, maximum part of the force is still in vertical direction, but there is a little part that is aligned in the x direction, which is aligned with the displacement d. Let's say this angle theta is 85 degrees. So in that case, fd cos theta would be fd cos 85. Cos 85 is very small quantity, so whatever this is, it is not equal to 0. So we will actually be able to push this cart a little bit, but this quantity would still be very small. It would be a very small quantity, so we can say that this quantity is still going to be very small, but it is going to be non-zero. What I really meant to say was the whole idea of dot product is to find out how much of a vector is aligned with another vector. और उसकी जो फिजिकल मोटिवेशन है वो ये है कि कई फिजिकल एग्जांपल्स में हमारे पास दो वेक्टर्स इस तरह आपस में एक्शंस में होते हैं कि वी वांट टू फाइंड आउट हाउ मच दे आर अलाइंड, so to find out the other quantities, as we did with the work done here. Now there are certain properties of dot product as well, properties or characteristics of dot product. Instead of just writing them down, I think we should be trying to actually see those in action और इसको खुद से हम conclude कर. सबसे पहला जो है वो तो ये है कि हमने अभी जो बात की थी वो ये था कि हम वेक्टर ए और वेक्टर बी दूसरा लिया था, एंड वी फाउंड आउट कि इनके दरमियान जो प्रोजेक्शन है दैट वाज ए बी cos theta. Now what if it was done the other way, where I was trying to find out what is the projection of A onto B. तो उसमें चूंकि हम A का प्रोजेक्शन देख रहे होंगे तो A cos थीटा होगा, और B के ऊपर देख रहे होंगे तो ये B A cos थीटा. Now obviously this is magnitude, this is magnitude. So A B cos theta या B A cos theta, both terms are actually same. So when we talking about dot product, it is actually that it is commutative in nature. Commutative का मतलब ये होता है कि जब आप 5 times 3 करें या 3 times 5 करें, it's same either way. The order doesn't really matter. So the dot product, maybe the order doesn't really matter. The projection of A onto B or projection of B onto A is actually the same thing. So this is A dot B is equals to B dot A. This is called as the commutative product. So scalar product is actually commutative in nature. The next thing that we need to see is again a very trivial fact, but it is important. Imagine I had a vector A like this. So let's call this B, and let's call this A. Now, what is the projection of B onto A in this case? We actually see कि इस केस में तो B का A के ऊपर कोई projection है ही नहीं. There is no projection of B onto A. Even if we try to do it, it actually comes at 0 point. इस केस में we actually see it. There is some projection of B onto A, but in this case, जिसमें ये 90 degrees का एंगल इन दोनों के दरमियान. This case is by the way called as when they are perpendicular. Geometry, this is called in geometry, this is called what we call as perpendicular, mutually perpendicular to each other. So in this case, vector B and vector A are actually mutually perpendicular to each other. The angle between them is 90. So what we see is that AB cos theta equals to 0, since theta is 90 and cos 90 is 0. But the point is that we even see this with its intuition as well. Is since B has no projection on A, there is no way we can project B onto A. So there is going to be no projection. And so this is the actually first property, which is when the two vectors are mutually perpendicular, the dot product is actually 0. A dot B is going to be 0, or B dot A is going to be 0. The next property that we have is when the two vectors are actually parallel to each other. So let's say we have two vectors A and B. This is A, this is B. And now if I ask you to find out the projection of A on B, you can actually see that there is a complete projection of A onto B. So in this case, the angle between them is 0. So A dot B is equals to AB cos 0. Cos 0 is actually 1. So A dot B is just going to be a multiple of the magnitude of both of the vectors, which is the maximum in this case. Obviously, cos 0 is 1. This cos 0 is 1 actually. And so that's the maximum that we can get from cos theta, right? So the maximum projection between the two exists when theta equals to 0, or when they're actually parallel to each other. So in case of parallel, when the two vectors are actually parallel, we get a complete projection, or A dot B is just going to AB. All right, so this is the second property. The third property that we have is just the opposite case, sorry, anti-parallel case, like we did in part 2. So in this case, if we have B as this way or an A as this way, so the angle between them is 180 degrees. So with theta equals to 180 degrees, since they are anti-parallel, so A dot B equals to AB cos 180, which is -1. So we get A dot B equals to -8. So in terms of magnitude, it is same as the second property, but we just get an extra negative sign, just to just imply that the two vectors are actually anti-parallel to each other. So the next example that we have is when we take a dot product of a vector with itself. So we have A, and we actually take a dot product of A with itself. In this case, A dot A is simply A squared. A squared in a sense, because you can say this is just the case of the parallel one, a special case of the second property, where the second vector A dot B is simply itself. We get A dot A equals to A square. And you already know that normally we would have AB cos theta, and if cos theta was actually 1, we would have AB. But since we are taking an example where the second vector is itself A, then we get A square. And you already know that in terms of vector, squaring something actually means that we are actually looking at the uh, length of that vector. So taking dot product of a vector with itself just gives you the length of the vector. We can also uh, write the scalar product in terms of the rectangular coordinates of a vector as well, or the rectangular components of a vector as well. So we already know that a vector A is just the sum of its rectangular components, which is ax plus ay plus az. So if we had two vectors and we wanted to take a dot product of them, for example, A and B, so A dot B is simply going to be ax plus ay plus az, and we multiply it with ay plus b. Sorry. So we have bx plus by plus. So these are the components of these vectors, and we've already talked about what the components really mean for a vector. So by the way, whenever we are talking about dot product, it is necessary that we multiply them component wise. So ax is going to be multiplied with a bx only, ay with by, and az with bz. If you're wondering why are we actually doing it, this really matters because if we multiply ax with by, then it is actually going to give an answer 0, because x component of a one vector and y component of other are actually perpendicular to each other. So since y is always like this and x is going to be like this, so they're always going to make an anti-degree angle. That's why they're going to go to 0. That's why whenever we're taking a dot product, the only terms that survive are the ones that they have same terms multiplying. So a dot b is going to be ax bx plus ay by plus az, which is equals to a dot b, or simply ab cos theta. All right. Now since we already know this is equals to ab cos theta, we can isolate the angle to find cos theta equals to ax bx plus ay by plus az b divided by what we have is the magnitude. All right. So this is one way to actually find out the angles of the two between the two vectors using the dot product as well. So these are some properties of what we call as the scalar product or a dot product. And just to give an highlight of it, the only thing that we did was to see was कि हमारे पास जो dot product होता है, scalar product होता है, it is only used to see if how much of a one vector is aligned with another, or how much of that vector is projected onto the other. And we have seen an example where we've seen how work done is really related to the dot products. anyways, आई थिंक एक और पॉइंट जो ज़रूरी है वो ये है कि why do we really call it a scalar product? You know, a scalar quantity is a quantity that just means a number, a magnitude associated with. For example, 5 is a scalar quantity, 10 is a scalar quantity. Why we call this product as scalar quantity is because we start off by multiplying or taking a product between two vectors actually. We start off with vectors, but the result that we get, AB cos theta, is actually just a number. So we end up with a scalar quantity. Scalar quantity in a sense that the number itself is a scalar. So that's why we say that dot product is actually scalar product as well. The next type of vector product is known as cross product, and we will see that in the next video. And I'll try to explain what's the physical motivation behind a cross product.